If there's one technology that defines the modern economy, it's the microchip. Microchips are used in countless products, from phones and computers to cars and washing machines. There are many technologies that have revolutionized human society, but none have driven such a rapid pace of technological development. Without microchips, there are no personal computers, there are no smartphones, there is no internet, and there is no AI. Microchips are probably the most complex and sophisticated technology that humanity has ever produced. A single microchip can contain over 30 billion transistors in less than a square inch of space. All of these transistors are arranged and connected in a precise three-dimensional pattern at a nanoscale level. Just as microchips are incredibly complex, the semiconductor industry that manufactures them and its supply chain are equally complex. This complexity comes from how precise and specialized every step of the manufacturing process is. This high level of specialization has led to significant interdependence between countries in the production of microchips. The semiconductor industry relies on multiple stages of international trade as raw materials, intermediate products, and production equipment are transferred among a wide network of companies. With how essential microchips are in enabling almost every aspect of the modern economy, it's important to understand the supply chains and production processes that go into making them. That's what we will cover in this video. We'll start by following the steps of the manufacturing process from raw materials and design to final products. Modern electronics require many different chemical elements as inputs. Some of these are the 17 rare earth elements. Rare earth elements are used for a variety of purposes. Some are used in batteries and magnets, while others are used in screen displays. Around 90% of all rare earth elements are processed in China. Most of these are also mined in China, and in particular in Inner Mongolia. Lithium and cobalt are also important elements, as they are key components of batteries. Over 60% of global cobalt production is in the Democratic Republic of the Congo. Around half of all lithium is mined in Australia. This is followed by Chile, which produces around 25%. Other important elements include gold, silver, nickel, copper, tantalum, and palladium. Many of these are used as connectors because of their conductivity and because they have anti-corrosive properties. The most important element, though, which is the primary material of microchips, is silicon. Silicon is a semiconductor that has special properties that make it particularly useful as the base material for microchips. Some specialty chips use alternatives such as gallium or germanium when higher performance is needed, but most microchips use silicon. Silicon is the second most abundant element on Earth by mass, but only some high-quality deposits can be used for modern electronics. Germany has many of these deposits and is the largest exporter of high-purity silicon, accounting for around 30% of global exports. The US is also a top producer and is responsible for about 25% of exports. China, though, is by far the largest producer of high-purity silicon. It is responsible for around 75% of global production. In the early 2000s, China only played a minor role in silicon production. It accounted for less than 10% of all silicon production. It rapidly increased this to become the global leader, and now produces around 80% of all silicon. Most of this is not high-purity silicon, and is used in other industries besides electronics, but China also developed its ability to produce high-purity silicon, and became the leader in high-purity silicon production as well. Even though China is the largest producer of high-purity silicon, it is also the largest importer of high-purity silicon. Most of the high-purity silicon exported by Germany goes to China. Demand for silicon in China is so high because China uses it to fuel its own semiconductor industry and to make intermediate semiconductor products that it exports to other countries. Silicon is used to create wafers, which are the base structure that microchips are built on. In what is known as the Czaralski method, high-purity silicon is melted and then a silicon crystal is grown and pulled from the melt. The silicon atoms within the crystal are arranged in a uniform crystalline structure, which is an essential property of wafers. Any impurities or contaminants can disrupt this uniform structure and cause defects, which is why high-purity silicon has to be used. Once the crystal has been formed, it is cut into individual wafers. A 12-inch or 300 mm diameter is the modern standard for wafer size. In the past, they were significantly smaller, but because larger diameters make more efficient use of the wafer's surface area, the industry has shifted to larger and larger wafers. Wafers then have to go through processes for cleaning, polishing, and texturing in order to prepare them for fabrication. In the 1990s, there were over 20 major companies that produced silicon wafers. Today, there are 5 companies that control over 90% of the market. Throughout the semiconductor industry, this trend has taken place. As manufacturing of microchips has become increasingly complex, there has been growing specialization and consolidation within each of the stages of manufacturing. Japan and China are the top 2 exporters of wafers. The Japanese company Shin-Etsu is the largest wafer manufacturer, with about a 30% share of the global market. South Korea is also a major producer of wafers. Many of these wafers are then sent to Taiwan and South Korea, which are the top 2 importers of wafers, where they are then used in the next step of production. As microchips have evolved over the past several decades and become increasingly complex, the process for designing them has also become more complex and specialized. Designers must first decide what properties they want out of a new chip, such as its cost, computing power, power consumption, and other aspects of performance. From there, they must go through several stages of design and planning to create a blueprint for the precise layout of all of the microchip's components. There are multiple levels to the design of microchips, and a variety of companies have developed that support the design process at each level. Some companies, like NVIDIA, are involved only in the design of microchips. They are known as fabless companies because they are not involved in microchip fabrication. Companies that design microchips rely on specialized software known as electronic design automation that helps them model and design their microchips. There are a variety of companies that create and sell EDA software, and the EDA industry is itself a multi-billion-dollar industry. Chip designers also rely on companies that provide reusable design modules known as core IP. These companies design specific components of microchips and license their designs to chip designers. This field is dominated by the US and UK, who together account for around 90% of the IP market. For the design industry overall, the US also dominates. It controls around 40% of the market, followed by South Korea with around 20%. After a microchip is designed, the design must then be imprinted and built onto a silicon wafer. This is the process of fabrication. In the early days of electronics, products were made by physically placing electronic components on boards and connecting them with wires. There is a limit to how effective this approach can be, as smaller and more powerful chips become increasingly difficult to make. Instead, a process was developed where the circuitry could be built directly into and on top of a semiconductor base. This is why microchips are also known as integrated circuits, because the circuitry is embedded into the wafer. The process to accomplish this is highly complex, involving over 500 separate stages. It takes several months to process a single wafer. Fabrication is done by using a combination of lasers, gases, and other chemicals to etch, clean, and deposit additional materials onto a wafer. The process for etching is one of the most technologically demanding. It uses a technique known as photolithography. First, a material known as a photoresist is deposited on the surface of a wafer. UV light is then used to weaken the photoresist in specific areas, and finally, the wafer is exposed to gases or wet chemicals that cut away or etch parts of the surface. A patterned mask is used when the wafer is exposed to UV light to create a pattern on the surface of the wafer. The mask only allows certain portions of the surface to be exposed to the UV light, while the rest is protected. These masks are what transfer each layer of the microchip blueprint onto the actual chip. The etching process is repeated many times along with a number of other processes. The wafer is repeatedly cleaned to remove any contaminants or intermediate materials and prepare it for its next steps. In addition, a variety of materials are deposited onto the wafer at different stages to serve as conductors, insulators, or for other purposes. Parts of the wafer also undergo doping, where other chemicals are implanted into it to alter the wafer's chemical and electrical properties. After going through many of these steps several times, the first layer of the microchip is built. The first layer is where most of a chip's key components are located. The billions of transistors in a chip are built in this layer. Transistors are what allow a microchip to perform the logic that gives it its computing power. Many of these steps are then repeated for the next layers. Microchips often have 10 layers or more. The lowest layer is where the transistors are, while the layers above this primarily serve to connect the transistors together and connect the different regions of the microchip. During the fabrication process, wafers are transferred on an automated assembly line around the manufacturing floor as they go from one piece of equipment to the next. This takes place in a clean room where the air is filtered to be 10,000 times cleaner than outside air. If even a single dust particle lands on a chip as it is being made, it can ruin the chip. Throughout the fabrication process, extensive testing is conducted to make sure that any problems are detected. In the beginning phases of a new chip's production, the manufacturing process is often modified and adjusted to correct for errors. Physical and chemical effects that occur during production can lead to misaligned layers and electrical failures. To fix these errors and make sure that chips are not defective, the patterns projected onto each microchip layer have to be carefully corrected and adjusted. Even after these adjustments are made, though, errors can still occur for a variety of reasons. All of the equipment that is used in these steps is highly sophisticated and is supplied by a variety of specialized companies. Test equipment manufacturers make the equipment that is used in testing the functionality and performance of chips at different stages in their production. Other companies make polishing machines, etching machines, slide machines, and lithography machines. The US and Japan are the largest suppliers of semiconductor manufacturing equipment. The US provides around 40% of the total, while Japan provides around 30%. This equipment requires constant post-sales support for troubleshooting, software updates, spare parts, and maintenance. A significant portion of equipment manufacturer revenue comes from these support activities. China has in recent years become the largest market for semiconductor manufacturing equipment, with around 30% of US and Japanese SME sales going to China. Revenues from the supply of equipment to China have grown rapidly and around tripled from 2017 to 2021. In addition to equipment, the fabrication process requires a number of chemical inputs. These include polishing materials, etching chemicals, photomasks, and photoresists. The supply of many of these chemicals is dominated by Japanese, Taiwanese, and South Korean companies. Most microchips are made by Taiwan, South Korea, and China. TSMC, the Taiwanese semiconductor manufacturing company, is by far the largest producer of microchips. It has a market share of over 50%. South Korea's Samsung is the second largest microchip producer, with around 10% market share. There are over 1,400 wafer fabrication facilities globally. Most of these are in the US, China, Japan, Taiwan, and South Korea. Only around 20% are outside of the Pacific region. These facilities vary greatly in the number and quality of chips that they can make. The most advanced microchips can only be made in a few places. The facilities that make them are highly complex and require the most advanced equipment. One of TSMC's most recently opened fabrication facilities cost around $20 billion. Microchips as small as 3 nanometers are currently made, while 2 nanometer microchips are expected to start mass production in the second half of 2025. TSMC, Samsung, and Intel are the companies that are able to make the most advanced chips. One of the key components for making the smallest and most advanced chips is extreme ultraviolet lithography, or EUV. The technology for this advanced form of lithography was developed out of a research collaboration between TSMC, Intel, Samsung, and ASML. The Dutch company ASML specializes in making wafer fabrication equipment. It has a monopoly on this new technology and is the only company in the world that makes EUV lithography machines. ASML manufactures these machines and then ships them to wafer fabrication companies. These machines are state-of-the-art, and their design and production is a very intensive process. ASML itself relies on a wide network of suppliers. It has thousands of suppliers throughout Europe, the US, and Asia. It also relies on companies that provide specialized parts that are needed in its machines. The German company Carl Zeiss SMT, one of ASML's most important partners, makes high-performance optics that form a key subsystem of lithography machines. ASML exports its finished fabrication equipment to a variety of countries, but most of its advanced equipment goes to Taiwan and South Korea. Taiwan and South Korea are responsible for a large portion of microchip fabrication, but especially that of high-end microchips. China is also a major producer of chips, but most of the chips China produces are less advanced. The quality of chips that are made varies widely between countries. Taiwan, the US, and South Korea tend to make more advanced chips, while China, Japan, and other countries make more basic, general-purpose chips. Countries that make more advanced chips need to import more basic chips, while those that make basic chips need to import more advanced chips. There is also variation in the types of chips that are made. There are basic logic chips, chips for memory storage, and chips that serve as microprocessors. Memory and logic chips are the most widely produced. These factors mean that there is a high level of interdependence among countries in the trade of microchips. They rely on each other for different types of chips. Once a microchip is fabricated, it still has to undergo several stages of processing before it is ready to be incorporated into a final product. Hundreds to thousands of microchips are built on a single wafer. Each of these is known as a die. These dies must be cut out and separated into individual chips. Finished microchips must also undergo an extensive amount of additional testing to ensure that they are functional and that their performance is acceptable. Despite the incredible care that is given to limit any contamination or errors throughout the manufacturing process, chips regularly have errors. In larger, more complex chips, such as those used as microprocessors, defects can make a chip unusable, or they can cause a chip to have a lower performance. Manufacturers sort these chips based on their performance. Those with the fewest defects and the highest performance are categorized and sold at a higher price, while those that have more defects are sold at a lower price. This process is known as binning. Even if these chips don't turn out exactly as they are supposed to, manufacturers are still able to make use of them and thus reduce waste. After chips have gone through further testing, they must be assembled and packaged in a protective casing. Some facilities fabricate wafers and also do some post-processing, but many facilities outsource this back-end production and send their finished wafers to specialized assembly, testing, and packaging companies. China and Taiwan have the most assembly, testing, and packaging facilities, while Japan is the largest supplier of the equipment used in these facilities. Taiwan also exports many of its finished chips to other countries for back-end processing. China, Singapore, and South Korea are the biggest importers of finished chips from Taiwan and have a big presence in the ATP industry. Other countries in Southeast Asia, such as Vietnam, Malaysia, and the Philippines, are also involved in the ATP industry and are responsible for a significant share of back-end processing. Even at this level of the semiconductor industry, there is a high degree of interdependence among countries. China is a top producer of the final goods that microchips are used in. China imports many finished chips and makes many of its own, which it then uses to make actual products. Microchips are used throughout the economy in a wide range of goods. Communications is the largest sector that uses microchips. This is primarily for smartphones and network infrastructure. This is followed by computers, which includes desktops, laptops, and data centers. Microchips are also heavily used by the automotive industry, and they are used in many consumer goods like TVs, gaming consoles, microwaves, and other household appliances. For many products, more simple legacy chips are sufficient and even preferred, while more advanced chips are primarily used in high-end electronics. Many microchips end up in consumer goods, but they are also used in the machinery and equipment used by various industries. In manufacturing, they are used for robotics and industrial automation. Hospitals also rely on microchips, as many types of medical equipment use them. The aerospace industry uses microchips in navigation and sensor equipment. The defense industry is also dependent on microchips, as they are used in missiles, vehicles, communication devices, and sensor systems. In the US, semiconductor sales account for only around 0.3% of GDP, but they are an important input for as much as 12% of GDP. Globally, microchips enable trillions of dollars of economic activity. While China is a top producer of finished products, its top customer is the US. China exports its largest share of finished products, both consumer and industrial goods, to the US. In the 1980s, microchip production was dominated by the US and Europe. At the time, the industry was more vertically integrated. Most companies both designed and manufactured their own chips. As the industry grew increasingly complex, greater specialization was needed. There was a shift towards fewer companies that were specialized in specific parts of the production process. Accompanying this shift in production was a geographic shift. In 1990, Taiwan and South Korea accounted for 0% of microchip production. By 2000, Taiwan accounted for over 22% of production, and South Korea around 13%. A new generation of more specialized chip manufacturers, centered in the Western Pacific, replaced the older generation. This change was led by companies like TSMC. TSMC developed as a foundry that specialized in making chips for other companies. Other foundries include UMC, Global Foundries, and China's SMIC. While the industry shifted toward more specialized production, there are still some companies that design and make their own chips. They are known as integrated device manufacturers. These include companies like Samsung and Intel. Samsung also serves as a foundry and makes chips designed by other companies. Another important category of semiconductor companies are the fabless semiconductor companies such as NVIDIA, AMD, and Qualcomm, which are only involved in designing chips. Overall, semiconductor production is highly concentrated among a very few large companies. These companies are well entrenched in the industry, as changes in production are often very costly. For example, if a design company wants to switch foundries, it is very expensive, as significant adjustments and testing need to be done to optimize the manufacturing process. Even switching material suppliers is a challenge, as manufacturers have to ensure that the new materials are up to their necessarily high standards for purity and quality. These sorts of changes can take years and often require several rounds of test production, which is why they are so costly. Although most manufacturing is centered in Asia, US companies have the largest share of semiconductor sales. Global annual sales went from $335 billion in 2014 to $627 billion in 2024. The semiconductor industry has experienced rapid, continuous growth, but with significant volatility. Many of the industry's final products have short life cycles, which means there is constant demand for new chips. But because chips are used in so many different products and industries, there can be fluctuations in demand due to shifts or disruptions in any of these industries. In recent years, the growth of the industry has especially been driven by the rapid growth of advanced tech and especially of AI. Despite this strong growth, there are still some areas of concern. The industry's biggest potential weakness comes from how specialized and consolidated it is. Only a few countries are responsible for most microchip production. At the same time, none of these countries are self-sufficient. They all rely on each other for different types of chips and for different stages of production. The US leads the way in producing advanced microchip designs. Taiwan and South Korea are specialized in manufacturing the most advanced chips, while China plays a key role in the production of high-purity silicon, the manufacture of silicon wafers, and the assembly of final products. Other countries, like the Netherlands and Japan, provide essential inputs to the production process. All of this interdependence and the high level of specialization that is required unfortunately means that the industry has the potential to experience severe disruptions if even one part of the supply chain is compromised. While this can happen as a result of natural disasters, probably the biggest threat is that of international conflict. The policies and actions of states, especially those of a handful of states in the Pacific region who dominate the semiconductor industry, can have a huge impact. Whether through wars or trade disputes, these countries have the potential to cause serious disruptions that would impact the global economy in profound ways. As microchips have been incorporated in countless products and sectors of the economy, any disruption to the supply of microchips would send shockwaves throughout the economy. States, though, have also become a major factor in the growth and further development of the semiconductor industry. Many countries have recognized the vital role that microchips play in the economy overall, as well as in the area of defense, and have moved to strengthen their role in this strategically important industry. In 2022, the US passed the CHIPS Act, which put $50 billion towards investments in semiconductor manufacturing. The European Union, South Korea, Japan, and India have all also put forward measures to promote their semiconductor industries through investment, tax cuts, and other incentives. China is also heavily invested in expanding its semiconductor industry and increasing its capacity to make more advanced chips. Over the past few years, the construction of new fabrication facilities has been dominated by the US, followed by China and Taiwan. While many countries want to get involved in the semiconductor industry or expand their role in the industry and their ability to make more advanced chips, they face many obstacles in doing so. The high complexity of microchips makes it difficult for new countries or startups to gain a foothold. At the same time, those that already dominate in the industry are working hard to maintain their advantage. Fundamental characteristics of the industry create forces that continually push for consolidation and specialization and will likely result in the industry continuing to be dominated by just a few countries.